Thank you very much for an introduction. So now we will come back to the topic of charge density wave and electron-phonon interaction that can be possibly caused by this kind of ordering. So at the beginning, I would like to mention my collaborators, theoreticians from Polish Academy of Sciences in Kraków, Professor Piekarz, Ptok and Kapcia, and our collaborators from University of Minnesota, who provides us perfect single crystals. And I would like to also thank the National Agency for Academics Exchange in Poland, who enabled me to be here and present you these studies. So let's start with charge density wave order. It's a charge order which coexists with superconductivity within copper-oxygen planes. It is incommensurate charge order, quite well defined. For example, we define temperature and doping dependence of this charge order for a simple mercury 121. It was observed in many cuprates, so it's like quite well-known phenomena. It appears within the underdoped part of cuprate's phase diagram, within the pseudo-gap phase, and it can strongly affect the electronic structure of cuprates. It can, for example, reconstruct the Fermi surface of the material in a big hole-like to the Fermi liquid-like to the small electron pockets within this violet area under high magnetic fields. But charge density wave order not only coexists with superconductivity, it also competes with superconductivity. It can be seen on this picture when the intensity of the charge order is shown as a function of external magnetic field. This intensity is growing, while at the same time superconductivity is of course suppressed. So these two phenomena are competitive to each other. However, we don't know clearly the mechanism of this competition, and that's quite interesting. That's why we are still investigate charge density wave order highly. So charge density wave order, it was can also affect lattice dynamics of the material, and it was shown in 2013 that the charge density wave order around the Q vector of charge density wave order, some anomalous softening of acoustic phonon modes appears. It was shown for yttrium, barium, copper oxide. And this softening, as it was said on Catherine's presentation, the softening is reported below TC at and also within the doping range where the superconductivity occurs. However, it was also shown that the electron-phonon coupling in this case, it's not strong enough to cause appearance of superconductivity of pairing. So we knew that the charge density wave order is not responsible itself for superconductivity. However, it was quite interesting, and people tried to explore the influence of charge density wave order on phonons more highly. And that's the point where it was also shown that the charge density wave order can cause softening of high energy optic phonon modes, and that was shown for a striped system, lanthanum, barium, copper oxide, and here we see the softening around QCDW. Also, more recent data are showing similar results, and that's data, that's RIX studies performed by Johan Chang's group, and it was also done for striped system, lanthanum, europium, copper oxide, and also around QCDW, a softening of high-energy phonon mode was shown. However, RIX studies are limited because of their resolution. The resolution is in the range tens of millielectronovolts. We know better, maybe not better, but different techniques that can also explore phonons more carefully. And that's why here I'm showing results for from inelastic X-ray scattering technique and anomalous softening of a high energy opting phonon mode for neodymium cerium copper oxide. It was reported nearly 20 years ago. Here it is signed by this green circle, and now I explain what it means. It means that this green high energy phonon mode softens around Q equals 0.2, while the second mode, the blue one, stays at the same energy. And it was reported for Q equals 0.2. Similar wave vector at which also QCDW was reported at 2015. So the question was, is it also true for not only for a striped system, but like for a very simple cuprate, that the phonon softening can appear because of the presence of charge density wave order? Is it a generic property of all cuprates? Is it like a generic electron phonon coupling? And this motivates us to perform our studies. So what we did was to redo this experiment and make it in for different temperatures and dopings also for the same compound, neodymium cerium copper oxide. Why for this compound? Because it's a very simple one with one copper oxygen plane for unit cell, and also another advantage is that for this compound charge order appears at very wide range of temperatures and dopings. So it's quite easy to follow charge order in this compound. So our approach was to choose two different samples, two different dopings, underdoped sample and optimally doped sample. Why? Because for optimally doped sample, charge density wave peak seen by resonant X-ray scattering, so quite standard method to explore charge order in cuprates. So this peak, charge density wave peak for optimally doped sample, is very prominent here. Its intensity is decreasing with temperature, but saturates around 300 Ks. However, the situation is different for underdoped samples, because here the charge order peak is not visible, so we have only a background visible here and a little bit of this peak at low temperatures. So yeah, we have two different regions for charge density wave order. And our approach was to compare the evolution of phonon dispersion for these two different samples. We also explored different temperatures because we see that charge density wave order is highly temperature dependent phenomena. And to do that, we went to ESRF beamline ID28, and that's the schematic of this beamline. But what is the most important for us is the resolution that this beamline can give us. It's about 3 millielectron volts, so we can really differentiate between different phonon modes. That's quite important for us, especially if we want to compare to the older data with lower resolution. And we explored phonon dispersion along copper-oxygen planes and copper-oxygen chains along this direction with transfer momentum as the one mentioned here. And that's example of our results. Results for optimally doped sample at 300 Ks. This part is a part of acoustic phonon modes, and the middle panel is for optical phonon modes. And here we also have the green and the blue mode. The green mode is shifting in energy towards lower energies, while the blue mode is shifting to higher energies, going up with Q vector. So it means that these two modes cross at point around 0.2, they overlap at this point, and in our interpretation there is no anomalous softening of the green modes, just crossing of them around 0.2, crossing or anti-crossing. So that's what we propose for this dispersion relation. And the dispersion relation is plotted here on the top of DFT data, because to be sure that our interpretation is okay, we performed calculations. And that's data for optimally doped sample. As you can see, the data follows nicely calculations, except of these two highest phonon branches, so the one for which the anomalous softening was reported. Calculations marked on this picture by gray lines are calculations for parent compounds, so antiferromagnetic one. And that was our first thought, that maybe that's the reason why these two branches doesn't correspond nicely to the calculations. And what we did, we changed a little bit our approach for calculations. We set u equals 0, j equals 0, and calculated once again. And at this case, for parent compound, what we get was two anti-crossing phonon modes. They have the same symmetry and anti-cross about a point of x equals 0.2. And that's exactly what is going on in our case. We also calculated dynamic structure factor for inelastic X-ray scattering studies, and the intensities that we got agrees very well with the intensity of phonon modes we measured. And what I can see more about this vibration of phonon atoms that we can observe here for these two branches is that the blue branch corresponds to the vibrations of all oxygen atoms, while the green mode corresponds to the vibrations of only oxygen atoms within copper-oxygen planes. So these are bond stretching modes. So we see that only oxygen atoms are involved in the vibrations which are drastically changed between undoped and doped material. That's kind of important information. Now I'm adding to the previous picture, I'm adding points for underdoped sample. And as you can see, they are at pretty similar places. So these two data sets are very similar within experimental error. So they can be named as a complementary. So the conclusion is we don't see any doping dependence. And at the beginning I've said that the charge density wave order phenomena is really doping dependent. So what I'm saying is that there is no influence of charge density wave order on the dispersion of phonon modes along copper-oxygen planes. And that's kind of important. But on the other hand, what we can say is that this anomalous anti-crossing is not really anomalous, it's just internal property of the material. And to prove that, we also performed temperature-dependent studies. And so we go through these points across the phase diagram of NCCO. So we compared inelastic X-ray scattering data for different temperatures and at different wave vectors, close to the CDW wave vector and also at other points. And what we see is that observed phonons are exactly at the same energy, at the same position. The only thing that is changing is the contribution from elastic lines, so the whole spectrum is going up here. But we, again, we don't see any influence of temperature on the dispersion relation, while the charge density wave is clearly temperature-dependent phenomena. So, again, charge density wave doesn't change phonon dispersion that we probed. However, we've seen some anomalous behavior. And here you have, once again, the blue mode and the green mode, but for different temperatures. And we've seen an anomalous broadening of this blue mode. And that's the picture in the middle. So it's temperature-independent broadening. And then we went back to the publications of Resnick from 2006, and what they are saying is that they predict that some dynamic charge in homogeneities can cause this kind of behavior, so broadening of phonon modes. And actually, dynamic charge fluctuations, dynamic charge density wave was seen in neodymium cerium copper oxide. It was published in 2016, and this kind of feature is visible and is temperature independent. And what is more, it's also coupled to paramagnum dispersion. So at the same time, this charge density wave, dynamic charge density wave and paramagnon contribution are increasing at resonant inelastic X-ray scattering spectra, and that's shown on these two pictures. And my message is that we are saying that this kind of dynamic fluctuations are causing anomalous behavior of phonon modes about the wave vector, of course, of these dynamic fluctuations. And we also, this phenomena of these dynamic fluctuations is generic property of cuprates. We measure that also for whole doped mercury 121. So to summarize my presentation, I've presented a new interpretation of the dispersion relation for model electron doped cuprate NCCO, and our interpretation agrees quite well with DFT calculations. I'm also saying that the static charge density wave order does not influence the dispersion of phonon modes. There is no temperature, nor doping dependence that is characteristic for a charge density wave order. I'm also saying that this anomalous softening of bond stretching mode is not generic property of all cuprates. It was observed for striped order systems, but it wasn't observed for any other system where the stripe are not present. And we see in our studies some indication of electron-phonon coupling that possibly is caused by dynamic charge density wave order coupled with paramagnons. And with that, I would like to thank you for your attention.